Yeah, hello everyone. Thanks Sthitadhi for the introduction. Thanks to the organizers for providing this wonderful platform for sharing my recent work. Actually, I gave a 10-minute talk on the same topic earlier this year, but we understand some aspects much better now, and the audience is also largely different, so I decided to talk on the same thing again. So this work was done with these people. So Jaswant is an undergraduate student, BSMS student in IISc, and Paul and Masood are faculty in CNRS and TU Dresden. And this is about this counterintuitive phenomena, which is what you see in the sketch here. What you have is some extended setup. And suppose we decide to actively cool one end of this, one part of this system. And the question is what happens to the other part? The two parts are coupled through this link. And our intuition tells us that, okay, so if I cool this part, the other end, their whole thing should cool down, basically. They're able to interact with each other. That's what the intuition says. But I'll talk about sort of a special class of systems where this does not happen. And actually the opposite happens. So what you find is that you cool this end, and you find that the remaining part actually heats up towards its most excited state as you cool that end towards its ground state. This is not restricted to cooling, so if you maintain this at some finite temperature actively, then you find that this actually evolves to the opposite temperature. So if this is some finite positive temperature, this goes to some finite negative temperature, which means the excited states are preferentially occupied and so on. I should immediately point out that this is not breakdown of any fundamental law of statistical mechanics, because this temperature gradient does not appear spontaneously. You are having to actively extract energy continuously from this part, and only while you are doing that, this remaining part will heat up. And basically the talk is to explain how this appears and what class of systems this applies to. And we hope this is also, I mean, I'll give examples of simple setups which possibly can be realized experimentally. Okay, so just to formalize the setup a bit more, the part that we will cool or heat, I'll call that part the lead, and the remaining part I'll call the system. And the question is what happens to the system. And a few years back, a specific modeling of this setup was done in this paper, where they took the lead to be a free fermionic lead. So like, for example, an XY spin half chain or something like that. And I think they took simply a tight binding model of free fermions, and they modeled these coolings and heatings by a Markovian Lindblad dissipators, which acts on this free fermion part. And they studied what happens to the system. And in particular, they showed that the sort of notion, the expectation that this reaches the same temperature as the lead holds, provided these conditions are met. So you have a generic setup, generic coupling, and the lead is large, such that its bandwidth, so single particle bandwidth in this case, is larger than the system. And also the system lead coupling is weak, and the cooling or the heating rate, this is dissipation rates here, are also weak compared to the Hamiltonian parameters. So the basic idea behind the first requirement is that the system should be able to transition from any one energy level to any other energy level by dumping the required sort of excess or lack of energy into the lead. These two other requirements might sound a bit counterintuitive. So of course, if you decrease the coupling strength and you decrease the dissipation rates, it will take longer to reach the steady state. But you can show that actually you require this if you want the system to reach a thermal state with respect to its own Hamiltonian. And partly the reason is that if you have a strong system lead coupling, that leads to boundary terms to the system Hamiltonian, which alters the energy levels. And also if you have a strong dissipation rate, that also broadens the energy level in some sense, so making the thermal state less accessible. So that's how these sort of conditions work. And you can show that this is where the expectation holds.
So electrons are allowed to tunnel from the system to the lead or not?
Yeah, I think the coupling here is just electron hopping between the two parts. Okay.
Shovan, I have a question. If you attach the lead to one edge, is the effective temperature in the system constant, or is there a gradient?
No, I think everywhere you get the same temperature. Yeah. Temperature enters to, yeah, so you choose the dissipation rate such that you maintain at the same, yeah. Yeah, exactly. Yeah. The system?
So the system lead coupling would also be Markovian.
The system lead coupling is just a normal Hamiltonian coupling. And so are you thinking of tracing out the lead to get some effective dissipation on the system, or? Yeah, I suppose if you, in this case, you might be able to trace out the lead to get some Markovian dynamics of the system alone, but I don't think they went through that route, but yeah. Okay, so this was established theoretically for these conditions, and then there was a series of works, including by Abhishek and Manas here, on finite size simulations, to taking a finite size system and finite size lead and asking the same questions here. So the dissipator they took was to acting directly on the single particle modes of the Free-fermion. Yeah. So either destroy or create a single particle mode, which is delocalized. So it'll be non-local in their case. Yeah. So and here also, I mean, the main story, I think, if I had to summarize the main findings, is that so cooling this way, cooling one part of the system never gets you exactly to the full ground state of the whole thing. So ground state cooling is always approximate, but you find that as you sort of try to satisfy these conditions more and more, so you increase the size of the lead, you make these weak, you find better and better cooling. And in particular, the first paper also suggests this as a way to sympathetically cool a many body system by cooling one end of the system. Yeah. Yeah. So in your paper also you found that as just one side does not work, but two sides, I mean, it gets better as you increase the number of sites over which you apply the dissipator. Even then it's not exact. Yeah. Yeah.
So, but here when you say lead is coupled to the system,
yeah.
you mean in the local sense?
Yeah. So this coupling is entirely local. So you can also think of the whole thing as your some spin chain, and you're acting the dissipator on the first few sites of the thing. Yeah. So the focus of these studies is that how efficient can we make cooling, how accurately can we cool down or get to the particular temperature state. And the topic of this talk is that there's a spectacular failure of this sort of common intuition if you have certain symmetry. If the setup is not completely generic, but there is some structure to the Hamiltonian, basically U1 symmetry of a certain kind, which is related to energy, and then you get the opposite. You get what I was describing in the first slide, heating by cooling and so on. Even if these other conditions are satisfied. Okay. So maybe let's first have a slide where we sort of mathematically, so why do we expect sympathetic cooling? Let's try to understand that in a via simple sort of perturbation theory on this setup. So suppose I have a single spin half, single qubit as my lead, single spin half, two-level system, and the system can be sort of an n-level system. I mean, this could be any number of levels here. And we have some coupling with some strength epsilon, Hamiltonian coupling, and you have some, in this case, I assume that the spin up is the ground state, so the dissipator I act, let's say I model it by a Lindblad, which is this S plus, which takes me from here to here with some rate gamma. So what I'll talk about, the Lindblad description will not be necessary, but this is just to understand in a simple case what's going on. So both these ingredients are required if you want to redistribute the population of the system among these levels. And so what you can do is, suppose the epsilon is weak, so then I can think of the eigenstates of the full setup in terms of the eigenstates, the product eigenstates of this part and that part, which will be perturbed by the coupling epsilon. Right? So if I think of the perturbed version of this state up across EI, where EI is some energy level of the system Hamiltonian, then this will have some perturbative expansion. So I'm assuming that everything is finite and there's no degeneracy and so on. Right? So this has some perturbative expansion like this. So this is the unperturbed version, just the product state. Then you have other product states appearing with different amplitudes, and then you have some second order correction to epsilon. And then for weak dissipation, this Lindblad will cause transitions between two eigenstates of the whole setup, right? So between two of these eigenstates. And actually, you can derive this from the Lindblad formalism, assuming that the density matrix is mainly diagonal in the energy basis. You can show that the transition rate is given by this matrix element squared, and that if you can see that this will select this Cij here, and perturbation theory then will give you this expression. And this expression is very instructive because it has a denominator which will vanish as soon as Ei minus Ej equals delta L. Delta L is the gap of the lead. Yeah.
I mean, why these transitions in the lead force a transition between only two states of the system? I mean, the coupling will not be diagonal in the basis of the system, so it can couple to several system states.
Yeah, that's true. So that's you're talking about this coefficients can be in general. I mean, this will involve all possible EJs for a given EI. So it can couple to. So I'm not assuming any particular form of the coupling here. So this EI can get coupled to all the other EJs.
So it's not from, if I understand, I and J are eigenstate of the system. It's
yeah.
not from I to J. It's from certain overall state, which is superposition to another.
Yeah, exactly. Yeah. So I'm taking, so these are supposed to be the perturbed versions of the product states. So this is so this will involve, EI, all the EJs of the system Hamiltonian in general, the perturbed eigenstates, so including the coupling, I mean. So the resonance structure, so the structure I was talking about is that you will get a very diverging rate to first order, to this order of approximation, where Ei minus Ej is equal to delta L. So delta L is some positive gap here, and this is the transition from I to J. So you can see that if Ei is bigger than Ej, so I'm going down in the spectrum of the system, then there's a possibility that this will become equal to delta L, and then the thing will be resonantly cooling down, basically. So what's happening is that this energy is being exactly compensated by exciting this lead from the ground state to the excited state, and that has a very large, so this is sort of Fermi's golden rule kind of expression that you get in perturbation theory. And so this will dominate over any upward transitions, because if I move upward, this Ei minus Ej will be negative, and so that will not cancel, the denominator will never be 0. And so those rates will be much smaller than the downward rates. So even with a single site lead, you can see that why we expect overall downward transition of the system going towards its ground state. And the main thing to notice is that these resonances will appear provided the numerator is non-zero, right? So the coupling is able to take the system down like this and at the same time excite this lead like that. Right, so this is basically an energy exchange between the two parts mediated by the coupling. And so the mechanism, this counterintuitive thing that I was talking about, happens when basically you can turn this thing off. So what if I don't allow any term in HSL, which is really able to exchange energy between the two parts? Right, so, and I'll give examples. I mean, this might look artificial at this stage, but I'll give examples where this is actually happens with not too complicated systems. So HSL is such that it will either take both the lead and the system up in energy or both parts down in energy. And you can write down such Hamiltonian couplings, but it will not really exchange. So it will not take this down and that up in energy. So if you prohibit, if you hypothetically could prohibit this process, then those resonances you can get rid of. And you have a possibility of getting other states. And suppose on top of that, I am continuously cooling the lead part towards its ground state, and suppose it has a unique ground state. Then what will happen is that this is, because of this active cooling, you are maintaining the lead close to its ground state most of the time. So whenever the coupling has time to act on the whole setup, it can take the lead up, and by the same token, it also takes the system up in energy before the lead is brought back to its ground state again by the active cooling. And so the system, all it can do is move up in energy whenever the HSL acts. And that's how it ends up, it can end up in the most excited state. Right? So continuously, the average energy goes up to its maximum energy. And so that's how and this continues only, this requires that you continuously cool. If you turn this process off, then the system, the lead cannot get back outside of HSL, and so this unidirectional flow will not happen. So actually you need the cooling for the system to heat up. Yeah, so this is what I was mentioning here. What happens if you stop cooling? If you cool it for some time and then I suddenly turn off this blue arrow, then because the HSL again cannot exchange energy between the two parts, it cannot get rid of the energy difference, the temperature difference between the two parts. Right, so the temperature gradient will actually remain, and I will show a numerical simulation of this thing. Due to the total energy conservation and due to the inability of the Hamiltonian to exchange energy, right? And so technically speaking, you can cool it by and heat it, cool this, have this thing on for some time, so heat it to some temperature and then turn off the process, and the system will be stable at that temperature, and the temperature difference between them will be maintained. And okay, so this is, I was talking hypothetically, you see that this argument does not really require a Lindblad kind of setup, as long as you are actively bringing it down towards its ground state, this argument should hold. And the nice thing is that this sort of setup actually can be realized in simple models that I'm now going to talk about. So the simplest case is just a two-site setup where the lead is a single spin and the system is also a single spin. Both can be spin half, but in this case I'm more general. I've kept it some n-level system. Some large collective spin can also be there. And suppose I have a spin exchange coupling between the two parts, which is Hermitian, of course. And another important thing is that I've applied opposite magnetic fields to the two spins. So this energy decreases with Sz, and this energy increases with Sz. And so, for example, in an experimental setup, if you have some two-level system, you can think about applying coupling the two levels with a red detuned laser in one case and blue detuned laser in the other case, which will effectively reverse the direction of Sz in the two parts. And once you have that, then you immediately see that this will exchange the spins, and by exchanging, this can either move both down, which is the first term, or move both up, which is the second part. So this will decrease the energy of both parts, this will increase the energy of both parts. But of course, if I'm strongly cooling actively the lead to always maintain it close to up, the first term is basically inactive, so it doesn't have time to act. Whenever HSL acts, only the second term acts, and that brings both of them up in energy, and then the blue brings it down again, and then you go to maximum energy. So it does not require any conditions on the energy level spacings between the two parts. Doesn't have to be uniform or anything, because I'm not relying on any resonance phenomena. So it also works for non-uniform spacing. And the main ingredients is that there's this quantum number, which is this Sz, which is inversely related to the direction of energy in these two parts, and the coupling actually preserves the total Sz. Yeah. What do you mean by energy? So this is just a Hermitian coupling between the two parts. So this either takes, so with respect to the sort of, yeah, so in that sense, I've killed off the energy conserving of the resonant terms. So the coupling I have with respect to the bare Hamiltonians of the two parts, it's taking either increasing their energies or decreasing their energies. So killed off the resonance processes, which are sort of the counter rotating. Yeah.
I mean, two things. One, I mean, if you write this coupling Hamiltonian system lead,
yeah.
Multiply it by some coupling constant, let's call it alpha.
Mm.
The sign of alpha is extremely crucial here. I mean, here you hit it because you assume that the coupling is 1. But
yeah.
if you write it alpha, then positive alpha or negative alpha will change your conclusion.
No, actually, it only matters on alpha squared. So I'll show some examples later.
Allow me to disagree. And the other thing is that concerning this conservation of energy, suppose you switch this coupling very slowly and switch it off very slowly. So let
Okay.
it act for some time. So you would think that under these conditions, adiabatic switching on and off, there is energy conservation. But this energy conservation means that the expectation value of HL plus the expectation value of HS plus the expectation value of the coupling Hamiltonian is conserved up to the non-adiabatic corrections. But it may happen that the expectation value of HSL increases or decreases to compensate for the effect that you're talking about.
Yes.
This is exactly why the sign of the coupling is important.
Yes, but if you have this constant cooling on, you can show that, irrespective, as far as the heating of the system part is concerned, that will be maintained. It's true that whether the coupling energy increases or not will depend on the sign, but the fact that this heats up towards its most excited state, that does not rely on the sign of the thing in front of the coupling. Yeah. So because I'm assuming that this cooling rate is stronger than this coupling, let's say, so this is always being maintained actively close to its up state. Yeah, let's say in the Lindblad picture there will be something like that. Yeah, Marcelo is.
So my question is exactly this. If the cooling rate is very strong,
yes,
you get into a Z effect.
Yeah.
Where essentially even the sigma minus sigma S plus
is
not that. So you will have a higher order perturbation theory.
Yeah. So actually this does not require the cooling rate to be large. So I'm just, so even if you have a non-zero cooling rate, you can convince yourself that this is the only steady state that you can have.
Okay, fine.
So it will
if
actually.
You go to strong coupling in that, you will have Z effect.
Yeah, that's true.
The heating will be extremely slow.
Yeah, that's right. But this is not required. I was just thinking for explaining the thing. Yeah, actually, so okay, so the one is I have flipped the sign of the fields, but the third one is also very crucial because if I had a coupling which like a Dickey type of coupling, sigma plus plus sigma minus times S plus plus S minus, then again the resonance terms will come into play and this effect will go away. So you need both the structure to be there. Yeah.
Very, very fast. Once you pop.
Yeah, so this will become active then, but you can show that still the steady state will be this. You can see that if I reach this state, there is nothing further can happen in this setup. And so if there is a unique steady state, it has to be this. Yeah, the coupling is pumping energy. Pumping through the coupling, basically. So that is the only term that can. So that's pumping energy in both parts, if you like, because of this. Yeah.
I'm only basically pulling out energy because I'm pulling overall.
Yeah.
And you're saying that I'm basically overall ending up with higher energy than I started with. I'm just wondering.
So this cooling is not a unitary process, so there's no reason for the whole energy to be conserved, right? So I'm just by whatever way I'm just bringing it down in energy, and then the coupling is just ensuring that the evolution happens this way. Yeah. Oh, so so I'm assuming okay, I'm mainly considering the case where the coupling is small. So the density matrix you can think is mostly like a product state of the two parts. So you can define temperature of this part very well, temperature of this part very well, but the whole thing, it's not a thermal state, if you like.
Between your Hamiltonian and the Lindblad,
yeah,
the steady state is the lead is in its lower level and the system is in its uppermost level.
Yeah.
So the total with respect to the total Hamiltonian,
yeah,
it's really far away from the
it's far away. Yeah. It's neither the ground state nor the most excited state.
So these terms should only occur in the ultra strong coupling. In the normal coupling, you should have de-excitation plus excitation.
No, so you can think of experimental setups where, so for example, if I have some, let's say, two transmon qubits where basically a photon exchange between the two cavities is happening.
As Smith mentioned, how's the energy
So this, you had some points? Yeah, so it's a combination of having this form and the cooling. Yeah, so if you can actually simulate, so within a Lindblad picture, you can simulate the dynamics and get some particular time evolution. So with these parameters, this is how the evolution looks like. So I'm plotting the energy of the system part, the right spin, which is simply measured by the magnetization of that spin. So I started from the ground state and it goes to the most excited state. And if you can also define the entropy, calculate the entropy of the system, and so the entropy is highest at the midpoint, where it's sort of uniformly, more or less completely mixed all the states, and then the entropy goes down once you reach the highest level. So in terms of entropy, it's not really, it's heating in the sense that you are increasing the average energy, and the entropy will have some non-monotonic dependence like this. Of course, you can stop it here, and then we'd have some infinite temperature-like state. Okay, and so this was for the case of just cooling. If you have both, you can also maintain the lead spin in some finite temperature state with respect to its own Hamiltonian by having both processes on with some relative rates, which ensures that the inverse temperature of the lead will go to beta L on its own. And then you can have the same setup. All I've introduced is added upward thing, and then you see that both these terms will be active. And you can basically show that therefore there will be both upward and downward transitions in the system as well. And these transitions are coming from these two parts respectively. And the rates you can show using that perturbation theory in the limit of weak coupling, weak dissipation, and so on is given by this up to an overall prefactor. And so, if you take the ratio of these, you can find that what temperature the system will go to. And the temperature simply comes out in this uniformly spaced case, it simply comes out to be minus delta L by delta S times beta L. So yeah, so this is what I meant by anti-thermalization. So this is some finite temperature of the lead, and this is going to the negative of that up to some prefactor. So this is more general than just ground state cooling. Okay, so this is, I was talking about a single site case for both the lead and the system. You can make the system a spin chain, which can be non-integrable, it can be integrable. And you can, so I'm still having a single site as my lead, the same type of coupling. And then the same mechanism can be argued in this case as well. So if I am always here, then again, the second term has time to act, has the chance to act on this, and it excites the first spin here. And if the system Hamiltonian is ergodic enough that it is able to take away this excitation into the bulk, then the spin can flip back to down again. And so this term can act again and increase the total SZ of this system part. I'm assuming the system Hamiltonian conserves the total SZ. And so therefore the system in that case will heat to all up state. And the all up state can be anywhere in the spectrum. So if I can apply some magnetic field in the Z direction to make it the most excited state, in that case I will be going towards this most excited state. Right, and so this was the case where the system conserves total SZ. If you don't conserve total SZ, if you add a symmetry breaking term to the XXZ Hamiltonian, then you see a crossover from heating to cooling when you're constantly cooling this lead. Right, so this is the symmetry breaking strength, and depending on the gap of the lead, which is there's just a single gap here, you get crossover from heating to cooling at different positions of BX.
This phase diagram presumably depends on the strength of your gamma.
Yeah, so this is assuming this rate equation picture, which assumes small gamma and small epsilon. Okay. So this is where it will go to in that limit. Okay. Okay, so let's make the lead also extended now. So assuming that's the Free-fermion lead, some XY chain, and again the same type of coupling. So you can have some generic system, and suppose that SZ is a good quantum number of the system, and the energy goes up, energy increases with SZ. Suppose you have that structure. Then again, you can get similar things. So I can use a Jordan-Wigner transformation. I can map the spin up to an empty site and spin down to a occupied sites for this Free-fermion or XY chain, and then the coupling would look like this. And then I can maintain the Free-fermion chain at some particular temperature and chemical potential. So let's say I'm always cooling down to 0 temperature. Yeah. No, so that was there for sympathetic cooling, which is I'm not requiring. Yeah. Okay. So so the lead spectrum for Free-fermion tight binding model is simply the cosine. So this is the single particle spectrum, and the dynamics then depend on where you are placing the chemical potential. So I'm assuming that I'm always cooling down to 0 temperature ground state at a particular chemical potential. So if the chemical potential is, if I place it completely below the band, then none of the states are occupied. And so I can only, the coupling can only produce hole excitations in the lead. And so this first term is not active anymore, the second term is active. And the second term also increases the SZ of the system, and so therefore increases the energy of the system. And so the system will heat to maximum SZ, whatever the energy of that state is. On the other hand, if you place the chemical potential completely above, then everything is occupied, and the coupling can only produce hole excitations. This was only producing particle excitations. So if it only produces hole excitations, the first term is active, and then the system is cooled down to its minimum SZ. On the other hand, if you place the chemical potential somewhere in between, then these terms, these states will be occupied, and these states will be empty. And so this will contribute to cooling, and these will contribute to heating, and you'll have some competition of cooling and heating in the system, and you get some intermediate temperature state, let's say. It doesn't have to be, I mean, I'm not saying there has to be a thermal state, but some intermediate state in the spectrum. Okay. For an n-level system, you can analytically solve this. Again, when the weak coupling, weak dissipation limit, you get these rates of going up and going down in the system state. And you find that as I increase this chemical potential, the energy, so the temperature of the system, it can be shown to be a thermal state using detailed balance. And the temperature, the inverse temperature increases from negative to positive. So in this region, you have heating. In this region, you have cooling. As you sweep the mu L up from bottom to up. Okay, so you see one interesting thing is that mu L, the range is -1 to 1, because that's the range of the cosine. But here I'm getting complete cooling even before I have reached the top of the band. And that is because the resonances start coming into play for some value of mu L. So basically once mu L reaches some level like this, such that this gap becomes equal to the lead energy spacing, then you can, so up to this state the particles will be occupied. You can create a hole at this state, and that will increase the energy of the lead by this mu L plus 1. And if this mu L plus 1 is equal to delta L, that delta L can be used to resonantly cool the system down one energy level. And so this is where, when this condition is satisfied, this is where the resonances are opened up, and the system, because I'm assuming a uniformly spaced system, it can cool all the way down resonantly towards its ground state. Right, so you hit a wall when this condition is satisfied, but below -1 you always get heating. So this is the crossover you get. So delta S has to be, it also depends on the value of delta S. It has to be between 0 and 2 for this kind of resonance to appear in the middle of the band. I think so. So I need the excitation to be spread, I mean, to be delocalized, to be taken away into the bulk of the system. Huh?
If you keep the bath at any low temperature,
Yeah.
this problem has been solved exactly that you increase the finite temperature of the bath.
Right.
And what Joel was raised, that to see that you would actually have to make sure that you look at the full spectrum of the system corrected by the maximum you have covered to the bath, and then you have a fluctuation.
Yeah. So when the two parts can be free-fermionic, but they're not identical Hamiltonian, right? So so in that case, you can solve it using third quantization, exactly, and you can check that these predictions are true for small weak dissipation and weak. Okay, I mean, we can discuss that later, because I mean, third quantization gives the same results and with different time scales. So maybe either something is different in the setup, or because this is what.
Sorry, just one. But third quantize here.
Yeah.
But third quantization holds only if your jump operators are linear in the fermions.
Yeah, it is linear.
Okay, but that's an additional constraint you are putting.
Yeah. So I'm modeling, I'm using the same setup as Podolsky, where the cooling and heating are implemented by either destroying or creating single particle excitations. And so your jump operators will be some linear combinations of C and C daggers in that case. Yeah, okay. So you can do slightly more things using this understanding. So the fact that this range of K contributes to cooling and the remaining range contributes to heating gives you some tunability of controlling heating and cooling in the system. So if you add longer range hoppings in the Free-fermion part, then you can tune the dispersion of the Free-fermion system such that you reduce the range of K, which gives cooling for a given value of mu L. And therefore, by reducing the cooling range, you would favor more heating in the system. And the curve you get is now pulled downwards. So now the heating range is increased from here to all the way up to here. So this, of course, this might be harder to implement experimentally, but I'm just saying that you can use this picture to tune the state to some extent. Okay, there are some corollaries. So using this consequence, there are some interesting things you can prepare in experimental setup. So let's say that you have a system which has a non-uniform level spacing. This could be some nonlinear cavity or some such thing. I'm assuming a very simple setup where the gap is 0.2 below this level and the gap is 0.1 above this level. So there's some nonlinearity in the spectrum. And then I can have a Free-fermion lead again, and suppose I tune my mu L such that this gap for resonant cooling is bigger than 0.1 but less than 0.2. Then I can resonantly cool down to this level. But here I will not have resonant cooling, I will have some competition of heating and cooling. And that can stabilize some intermediate state like this. And if you favor heating more, then you can make this peak sharper and so on. You can also actually make this peak sharper by increasing the lead hopping and etc. So this is some photonic Fock state that is of interest in quantum optics. You can also have cases where you get different symmetry sectors of the system heating up while the system overall cools down. So a subsector heating can persist with global cooling. And this happens because you can get resonant cooling between the bottom of the next band to the top of the current band, because that gap is small. And so you get preferential occupation of the top levels of each band. And they then form like an n-level system, so they can be, depending on the chemical potential, they can be cooled or heated following this curve as you sweep the chemical potential through the dispersion of the lead. And finally, you can have the stable temperature gradient as well. So this is, I was mentioning previously, here I've taken just a single XXZ chain with opposite magnetic fields in the two parts, and I've cooled down this part up to some time, and then I've stopped the cooling. And you see that the lead maintains a positive temperature and the system maintains a negative temperature after the cooling is done, because there can be no exchange of energy by the coupling. If you break the symmetry in the coupling, you don't conserve SZ anymore, then richer things can happen. You can sort of open up these resonant processes, so you get a competition of heating and cooling again by this breaking of U1 symmetry, and then you can get some phase diagram like this, where depending on delta S and this symmetry breaking term eta, you can either get heating in the red portions or cooling in the blue parts. Which, you can isolate the effects of resonance and symmetry in this nice case. Okay, so that brings me to the end. So this is sort of what I'm calling anti-thermalization, just a catchy name. So this is some breakdown of expectation of traditional thermalization due to this conserved quantum number in the structure of the Hamiltonian, which can allow you to produce exotic states and can be realized, I hope, in experimental setups. I have not talked about modeling of these setups, but we can discuss more. So this we plan to put up shortly in archive. Thanks for your.
Thank you, Shovan. We had quite a few questions, but maybe we have time for maybe a couple of questions.
So if I understood you correctly, you needed the coupling between the lead and the system to be symmetry preserving.
So yeah. So both the Hamiltonian, so HS, HL and HSL all conserve SZ.
So you took a particular form of the coupling, like which is sigma minus S plus.
Yeah.
Does all of this survive if you add other symmetry preserving couplings? Do you have any study on that?
Other symmetry preserving coupling, so other SZ preserving terms. I think so. If you, for example, if you add SZ, which is this XXZ chain I was showing. So here the coupling also has a ZZ coupling.
No, between the lead and the system.
Yeah. So this bond, between the two parts. Here, I also have a ZZ term. I think even if you add other terms which preserves SZ and preserves the directionality, then it should hold.
Yeah, thanks for the interesting talk. So, so you had a Free-fermion in the system, right?
No, system can be anything actually.
It can be anything. So my question is that, do you have an intuition that if you do put an interaction term in the fermions, like the examples you showed were all Free-fermion systems?
No, the systems were XXZ chains mostly.
Yeah, exactly. Yeah. But suppose I put a four-fermion interaction there.
Within the system, Hamilton.
Yeah, within the system. Do you think it would be a bit more efficient in terms of, in terms of dissipating the excitation at the left edge?
So in some sense, the more ergodic it is, the better it can dissipate the excitation, the better it should work, basically. So if you have some disordered system, that can cause problems because you cannot, the excitation might be locked in and cannot spread everywhere. So, yeah. Okay.
Thanks.
Shovan, one very quick question. So in the lead, when you were doing this cooling thing, so to simulate this in your numerics, do you put in a process or what do you do there?
So I think for numerics, we use Lindblad.
Just the Lindblad, but with one coefficient being smaller than the other or something like that? I mean, because you had this S plus and S minus, right? So one of the terms were
yeah, so if you want to maintain it at some finite temperature and not just cool it to the ground state, then
so you just put it at some finite temperature.
Yeah, you'll need both the direction. So there's separate Lindblads for up and down.
There is a system with two parts. You are cooling the left part and the right part becomes hotter.
Yeah.
Where does this energy come from? It comes from the leads.
It comes from the combination of coupling and cooling.
The particular form of the Hamiltonian of the coupling of the lead.
Yes.
Sorry, not the lead, the contact.
The coupling, yeah.
So the contact is what gives rise to the change in energy of the system. That's not very typical. No, we don't think of the contact as a source of energy.
Yeah, so typically contact exchanges energy between the two parts. But I'm saying that, so that is the more generic case, but I'm saying that you can have systems where you kill off that part and you only have non-resonant processes between the two. And that can change the total energy of the whole Hamiltonian.
Okay, but I would not call it contact.
Okay. So these processes will be very slow because of, much slower than resonant processes.
Just a minor question of interpretation, but I guess I would say, if I didn't have the Lindblad and I just looked at the Hamiltonian of the full system, that would conserve its energy, evolution under that. So I guess I would think that, if I imagine acting with the contact for a little while and then evolving and acting with the contact and so on, at like low density of contact events, then it seems like what the contact must be doing is not actually lowering the many body. I mean, it lowers the energy of the left half, but even the process induced by the contact is not really cooling if you look at the global system.
No, it's actually raising the energy of the total system.
Yeah. So in that sense, energy is flowing in from the contact rather than flowing out, even though locally it looks like it's cooling.
Yeah.
Yeah, hi. So let me replace this entire setup with a single atom and a cavity on the right-hand side.
Okay.
And I start with the ground state where the atom is de-excited and the cavity is empty. So what does it mean now?
So it depends on the coupling between the atom and the cavity. So
say it's a weak coupling, as you mentioned.
Yeah, but also, what type of coupling? So if you have some terms where it can produce excitation starting from a vacuum of the whole thing, then so you'll have some E-dagger sigma plus kind of term in the coupling.
But in the terms that you mentioned, you only have sigma minus, which is a de-excitation, and S plus, which is an excitation.
No. So I also had opposite magnetic fields in the two parts, right? So it would
Okay,
actually.
so that was not shown in the
No, so
picture that you flashed? Because I could not see where the energy.
So this one. So here, this part decreases the energy of both, and this part increases the energy of both.
But I think sigma minus means de-excitation of the two-level system, and S plus means excitation of the latter,
so
right?
I have opposite detuning.
Okay, so that is changing the entire thing
here.
here.
So
Okay,
it changes the direction of
so
energy.
sorry, that's what I was really getting confused about. Okay.
I'm curious, is it understood, it seems like this U1 symmetry is not strictly necessary, but very helpful for the phenomenon. And is there a way to think about it in terms of, if I didn't have the U1 symmetry, I would just have a Gibbs ensemble with one parameter like temperature or beta. And now I've got like a 2-parameter ensemble. I mean, I guess for a thermalizing system, we sort of know how we put in the U1 and how that would matter. And I'm curious, is there some way to understand what's going on just in terms of the change of the ensemble?
I don't think we understand that to that level, but it's I mean, yeah, so far U1 symmetry, all we have worked on requires U1 symmetry, but I mean, ultimately it depends on the nature of the couplings, conserving some quantum number which is directed to the direction of energy in the two parts, and whether you can get that outside a U1 framework, I don't know at the moment.
Okay, let's thank Shovan and Rubal as well.